Okay, once again, welcome. So, assignment 1 has been uploaded. This is the deadline next Monday, 11. So, before the lecture, okay? So, you don't spend my lecture working on your assignment. And you have to submit your work online. And for you to practice, I also uploaded the honesty form, which you have to submit anyway. Okay, so if you are not familiar with this interface, this is your chance to practice. You treat this as your assignment 0, the honesty form, and then submit to me using Blackboard. Okay, and the other thing is exercise classes start this week. We have 3 slots, and you will see the questions soon. And you are encouraged to practice because these are really additional questions to help you learn. And all the I try to make the interface very simple. So this is my page on Blackboard, and everything you need is here. Is in the second whatever this one. Sorry. Yeah. Okay, you can find everything inside. You get the lecture notes and the assignments. Yeah, and in the assignment folder, you will find the form. I have already received some. So for those of you who hasn't submitted, please do that soon. Okay, this is essential anyway. Okay, I will start by asking if you have any question for me. Anything? Okay, I don't see any. Okay, so let's start right away. Okay, last lecture, we stop here. So this is a little bit of material left in chapter 1, which we can finish off rather quickly. So this is about the 0th law of thermodynamics. And the sentences are here. So this is, some people think this is very important. It's really so important that you have to write it as a law. And some people think this is so trivial that even if you write it as a law, it doesn't deserve to be the 4th law. So they call it the 0th law, which is obviously come after the 3 laws of thermodynamics. Okay, so the reading is this. Remember, you will see all these laws of thermodynamics, and these are all based on experiments. You see, they write it as a law. And how do you really prove it? This is not easy. You have to really do experiment. You cannot prove it from mathematics. You cannot write equations and then prove that this law must be true. Okay, so in some sense, this is a little bit like more like the hypothesis, or maybe a better word is postulate. And in statistical mechanics, you will see the word postulates. Okay, so here, this is the writing. So if 2 systems are separately in thermal equilibrium with a third, then they must also be in thermal equilibrium with each other. That's it. This is the full content of the law. So usually this third system is what we call the thermometer. Okay, so if you would like to call, if you want a simpler, even simpler statement, you can simply say the 0th law of thermodynamics basically say thermometer works. Okay, it establishes this property. Okay, but with this, we can do something fun. So be careful. I do not assume much more than this. I basically start from here, and I want to establish one property for you. So this law establishes something called the temperature. Establish the notion of temperature. and give it a little bit of meaning from now. Because we already discussed for thermodynamics, we do need this concept. We need to talk about temperature in addition to mass, length, whatever that you learn in classical mechanics. But here we do have to add in the notion of temperature. That's why sometimes people think this is really fundamental, really important. Okay, so I'm going to do something a little bit maybe not familiar to some of you. I'm going to do some analytical argument, which you can find in my notes anyway. But in the past, some students are not too comfortable with this. So let me try to explain this for you. So I'm going to do something like this. I'm going to pick 3 systems. I'm going to call this system A, system B, and the reference system, the third system, I'm going to call it system R. This is usually my thermometer. Okay, so I'm going to assume this, this system is some kind of piston cylinder type system, an idealized one, which I can ignore the friction. Okay, so all these systems I'm going to assume they take the shape like this. They take the shape of a piston cylinder. So this is my cylinder, and this is my piston, and I'm going to ignore the friction. So for such a system, I'm going to put some gas, some fluid inside, and we know from week 1, such a system can be characterized by some function of states. And here I'm going to call them, I'm going to choose pressure and volume, which is easy to imagine. Okay, so the thought experiment goes like this. I'm going to start with R. I'm going to initialize my experiment. I'm going to prepare my experiment such that I want my R to take the value of PR and VR, the fixed value. Okay, suppose I'm able to do this. Don't ask me how, just imagine I can do this. I want a particular state. I'm very demanding. I want this system R to describe a particular state, and the description is given by PR and VR. Okay, and I'm going to bring in A to be in thermal contact with R. Okay, so in this case, you know, if I put 2 systems together, everything can change, but I'm going to demand that whatever changes happen to A, I don't care as long as my R remains at PRVR. Okay, so this is, I'm going to take A to be in thermal contact. Thermal contact with R, and if let's say if A takes some value of, so A is a similar system, piston cylinder system, so it can be described by VA, PA. Okay, so if the pressure of A changes to a different value, V has to be adjusted accordingly. Okay, so I'm going to, and in this case, you get a pair like this, right? So the state of the system A is described by this coordinate. So if you have different state PA, VA prime in equilibrium, in thermal equilibrium with PR, VR, then you get a different pair. And all these will be lying on the same curve. And this is called the isotherm. Okay, so remember, I want this to be fixed. Okay, so suppose at thermal equilibrium, we are able to describe our system. We can examine our system A and R in thermal equilibrium. When they are when they reach thermal equilibrium, so at thermal equilibrium, now I have to look at 4 variables. I will have my PA, VA. Okay, at thermal equilibrium, suppose this is the one I choose to, after all this variation is stick to this PA, the value of PA, VA, and this PR, VR is what I demand it to be. These quantities will satisfy a fixed relationship. So I'm going to write it as, I'm going to write it like this. So this 4 quantity satisfies some relationship which I do not know explicitly, but I know there must be some function of 4 variable, PA, VA, PR, VR equals 0. Okay, so this is my equation 1. Okay, you have the chat, right? So I'm going to ask you a question. You just have to type the numbers. In equation 1, how many independent variables do we have? I want to see your answer. If you are too shy to type to everyone, at least type to me. Okay, my question is this. Now I set the scene for you. Okay, at thermal equilibrium, I must have this relationship describing the relationship, the relationship among these 4 variables. Okay, how many independent variables do I have? Any more? Okay, I get 2 different answers already. That is beginning to become very interesting. Just look at this mathematically, okay? Equation 1, look at equation 1. How many independent variables do I have? And if you answer this correctly, mathematically, this will also help you to understand the physics we set up here. Okay, now I get 3 answers. That's getting very interesting. I should have a board, but then I haven't prepared. Okay, just 10 more seconds. I can do a quick statistics. This class is quite shy. Everyone is writing to me in private. Okay, I get the answer from 2 to 3 to 4. Okay, then this is no. The correct answer is 3. Okay, so here you have 3 independent variables. Think about this again. So one way to look at this is to again look at the equation of state for 1 mole of ideal gas, right? Last time we talked about this. So this is an aside which I would like to not to interfere with my whiteboard. I'm gonna put it here, small for you. Okay, so this is 1 mole. So I'm going to suppress this n. Okay, this is the equation of state for an ideal gas. So I get the answer from 2 to 3 to 4, but nobody say 5. If you luckily nobody say 5. If you solve this, you can actually say this is PV. Now this is not that easy to write. So if I say this is R T divided by V, so this is a function of 2 variables, right? Right, so I can write this as P as a function of T and V. Okay, I can also move everything to the other side. Then I can write this as some function F of P, T, V equals 0. So this carries the same information. It's just I was not explicit with the function F. Okay, so when you see something like this link together, it means you can in principle solve for one of the variables as a subject. So there are 2 independent variables. R is a constant. So here you do have 3 variable. So I can solve it. I can choose one I want to solve. So let's say to be consistent with the lecture notes, this is really a function of 3 variables. Okay, so I can choose P sub R as my subject, and this will be a function of 3 variables. Okay, so I have PA, VA, and VR. Okay, and I can repeat the same game with, I take A to be in thermal contact with R. Now, the statement of the 0th law means I can take my R away and move to B. I can take B to be in thermal contact, with system R. Okay, so I repeat the same game. I will have the other function f of BR like this, and then I will have my PB, VB. I don't want to write it again. So this will give me the same result, right? I can simply change all the A's to B. I can have another thing like this. Okay, now these are both with the subject of PR. So these two are equal. I can have f of AB, f of AR of PA, VA, PR, f of BR. Okay, this I'm going to call equation 3. Okay, this comes from the fact from these 2 lines. Okay, now I'm also now how many independent variables do we have here now? Once I write this. Okay, from 3, I'm going to do one more thing. I want to solve for PA. Okay, I want to solve for PA. I can choose VA, but I'm going to solve for PA anyway. Okay, so from 3, if I solve for PA, and then the remaining variable will be independent. I have VA, VB, and then I have PB and VR. Okay, all these are unknown functions, but they are true, mathematically accurate. Okay, so I reached this point now. Okay, what can I do next? What I will do next is to apply 0th law. Okay, so I apply 0th law. Remember, now I look at the thermal equilibrium between A and R. Then I look at the thermal equilibrium between B and R. But the 0th law has a starting point of, the 0th law tells me once I do that, I should also examine the thermal equilibrium between A and B. Right? Because the law say that if A and R are in thermal equilibrium, B and R are in thermal equilibrium, A and B should be in thermal equilibrium. So I'm going to look at A and B now. So now system A and B are in thermal equilibrium. Repeating the argument earlier, I would have, in this case, since they are in thermal equilibrium, the pressure and volume of each system satisfy another relationship, which I'm going to call it F sub AB. So I have PA, VA, PB, VB. And this is the same expression you saw earlier. Okay, I'm going to next solve for PA. I'm getting a little bit bored, so let's almost there. So I can solve for PA. Okay, so this will be VA, VB, and PB. Okay, same thing as earlier when you see the F of AR. Okay, I think this is the key here. Now here we can already see something, we can already get the conclusion we want. Okay, you look at 4 and 5. Now you look at 4 and 5. What do you discover? So you look at 4. 4 tells you the pressure of the system A is a function of 4 variables here. Okay, but 5 tells you the pressure of system A is only a function of 3 variables. Okay, so if both of them must be true, this VR must be cancelled out somewhere. So this VR must be cancelled out somewhere because here there's no VR. Okay, so where do you cancel this? You have to trace back to the step before. So this comes from 3, right? 4 comes from 3. So you realize, okay, in this case, this VR, this is still true, right? F of BR, the right hand side can indeed have VR, but they must be cancelled out at this point, at this line. Okay, so the left hand side and right hand side can independently contain VR. Maybe here you have a 3 VR square, for example, and here you also have another 3 VR square, which you can cancel. Okay, so here is our conclusion. So if A and B are in equilibrium, you can, if A and R are in equilibrium, B and R are in equilibrium, then Zero's law say N and B must be in equilibrium. So in this case, you can extract this line here. So this line tells you, you must have a relationship between PAVA and PBVB. They are separately on each side of the equation. So I'm going to, I don't want this anymore. I'm going to change the symbol. Okay, it's basically just a rewriting of this. I'm going to call this this function PA. I'm just rewriting this a little bit just to emphasize the importance. So after I cancel out my VR, I will have this relationship. Okay, and I can repeat this process by introducing system C, system D, system D. So as long as they are all at thermal equilibrium, I can generalize this to more terms. Okay, this phi, capital phi, I can generalize it to 5 sub C, sub D, sub E. Okay, so in this case, all of them will be a function of P and V in the general case. And I choose to call this, how do I call this? I'm going to call this the temperature. Okay, so from this analytical argument, we can say that if two systems are in thermal equilibrium, there must be one common parameter, a common function of state that describe both systems, and that parameter is called the temperature. Okay, or actually the more precise word is empirical temperature. This is this establish the notion of empirical temperature. Okay, so I don't know whether you have seen this before, but in those classic thermodynamics book, this is always there. If it's the first time you see this, you might feel very strange. And most people, now, if you don't know how many, the question as I ask you about how many independent variables is very important to get to the bottom of this. Some students, if they mess up that step, they will find this argument not easily acceptable. Okay, so this is from zeroth law. People always say, what do you gain by writing down this zeroth law? The thing you gain is because of the zeroth law, there must be one quantity which is unique when you have thermal equilibrium, and that quantity is the temperature. And this follows from the zeroth law. Okay, any question about this? Okay, so you have the zeroth law, and then most people, about the questions I asked earlier, most people get it right. I don't have statistics, but most people get it right. And a lot of students also say 4. Okay, now you have a notion of temperature. The next thing you ask yourself is, can you build a thermometer? And this is something you learn. I think you learn in first year and second year physics. You learned before. So I'm going to be very brief. And how do you build a thermometer? The zeroth law doesn't tell you how to do that. It only tells you there's something called temperature. And to really have something useful to determine what is this temperature, you need some scale. Okay, so to do this, you need a scale. You need a temperature scale. And how do you do this? How do you build a thermometer? You need a temperature scale, and then you need a thermometric property. Thermometric property. And to establish the scale, if you talk about a scale, there are a lot of knowledge going into this, right? Is a scale linear? Is a scale non-linear? And how do you put the scale on your on a temperature axis? So you need also first you need to specify whether the scale is linear or non-linear, or whatever. Then the most importantly, you need the reference points. Okay, so in assignment 1, you are asked to look at one thermometry problem. Very simple. And you will think about this again. I have some notes written, not too long. You can have a look and think about this. So I'm only going to maybe give you some example of the thermometric property. What can it be? And how do you build a thermometer? This is actually something. This is a big business actually. How do you have a good thermometer? For example, those people working on low temperature physics, like my group works on low temperature physics, so we do need some kind of thermometer. And the group of Professor Wang Dajun works on Bose-Einstein condensation, and there they are claiming nanokelvin or hundreds of nanokelvin, very, very low temperature. How do they measure those temperatures? Okay, so this is a rather important business. And I'm going to give you about the BEC. There we might have, if we have time, when we talk about statistical mechanics, we might be able to appreciate that. So here, I'm going to give you 2 examples of how to build some thermometer that doesn't go down to such a low temperature, but low enough to be important. So for example, 1, you need to think about thermometric property. One example would be, for example, I can use the resistance, the electrical resistance of some metal. Okay, so I'm going to draw to you. This is not a solid state physics course, so I'm going to just give you the answer. Now, suppose in solid state physics, we know something like this. If you cool down a piece of metal, the resistivity goes down, and eventually it will level off like this. Okay, so this is not the primary thermometer as such, because you do have to calibrate this. The argument might sound circular to you, so be careful. So suppose I'm able to calibrate my thermometer to some other more primary source. For example, something that I can use the property of the ideal gas. I put my resistance thermometer in thermal contact with that. I will be able to calibrate the temperature, and then I measure the resistivity. Okay, what I want to do is to have a thermometer that I can sell as a product. So this can well be what I can calibrate, and I can tell you if you measure a certain resistance, I will be able to read the temperature. Okay, so the way to think about this kind of product is this. I'm going to have a very expensive equipment to measure this axis very accurately, and then from here you read the temperature. So this is the temperature. Okay, and this will be my thermometer. This is something we use quite often, actually. We spend some money to buy some very high quality well-calibrated metallic resistors, if you like, and that allows us to read the temperature. Okay. Now, the reason I draw this here is because this is a very nice example to tell you this thermometer eventually will fail. Okay, again, using the chat, please tell me when it will fail. You can type to me privately, and I'm going to spend 1 minute on this. Now, this thermometer, this particular example, this thermometric property is very good. It's very good. And it's rather cheap, relatively cheap. I can buy this. It will be several thousand Hong Kong dollar, but it will fail. Okay, again, nice. More answer. Now, let's ignore the heating. Okay, good. I get 2 answers. They are very good. Okay, I get 3 answers. They are correct. Okay, this thermometer will fail here, because if you measure this resistance, there is no sensitivity. Okay, suppose you measure this value. Tell me what is the temperature. If I expand this curve, you will see there is some curvature. That is okay, you can still read this, but the error will become big. Suppose your measurement has an error, which I just draw schematically as a vertical error. That will translate into the error in temperature by the local slope. Okay, so if I have an error here, that will translate to the error in temperature because of the slope. So when the slope becomes flat like this, the error is huge. Okay, so this is not a good thermometer when you approach very low temperature, but low temperature, it depends. This we are talking about of the order of 10 Kelvin, already quite low. Okay, so good. I saw at least 3 or 4 answers there are very nice. Okay, second, how do I fix this? Again, if you have some thought, please share with me. Suppose I have the setup, the measurement setup to measure the resistance and to read the temperature this way. Can you propose another product that can help me to solve this problem? Okay, I get some answer again. It's nice. It's nice. More. I don't know why someone say alcohol, but then now suppose I still want to do my measurement here. What is the cheapest way to fix this problem? Okay, so the cheapest way is to buy another thermometer, but that thermometer will have this kind of property. Okay, so actually I want to draw something diverging. Okay, and you can actually achieve this. Let's say if I can do 10 Kelvin here, if I can find a thermometer that give me this kind of thermometric response, I will be able to have a good sensitivity at low temperature. And this can be achieved, for example, by using semiconductor. Okay, the resistivity of the semiconductor goes up when you cool down. That is because at low temperature, semiconductor has a band gap, so you don't have enough charge carrier moving around. So the conductivity has to drop. Conductivity drops means resistivity shoot up. Okay, so this is, for example, ruthenium oxide. Okay, so let me say a bit more. This is metallic at the top, and this is a semiconductor. Okay, I think this is enough. If you want to learn more, you can read Blundell and Blundell, page 34. Okay, so there will be a little bit more information for you there. Okay, and just very quickly, if we want to, one important scale that is important for this course is the thermodynamic scale, which is also called the Kelvin scale. We are already using it a lot because this is, I already use Kelvin scale, 10K. But maybe it's important to remind yourself how to get this scale. So this scale, you get this scale. What is the thermometric property for establishing this scale? You need ideal gas. So this is based on the property of ideal gas. In particular, what aspect of the ideal gas? You look at the volume and the pressure. Okay, so you can write the Kelvin scale, the temperature determined by the Kelvin scale to be based on the equation or state of the ideal gas. Okay, so this is if you take 1 mole. If you take 1 mole of ideal gas, this is, and use it as your thermometer, and suppose you are able to measure the volume and the pressure, that will give you the temperature. Okay, but there's one catch. If you take different types of gas, that's the point. You can use any kind of gas. There's one important constraint, and the constraint is you have to be in the dilute limit. The reason you want to be in the dilute limit is you don't want to worry about the interaction between the gas particles. That is to say, you don't want to worry about non-ideal gas. Okay, so these will establish the temperature scale, and this temperature scale is called the Kelvin scale. And how do you choose the reference point? You choose the reference point like this. You choose this R. Now you know it's gas constant, but how do you get the gas constant to begin with? Actually, you can do some kind of experiment like this in undergraduate lab, and that will ask you to determine R. And what is this R? How do you determine? So this R is chosen such that you have 100, exactly 100 units between the ice point and the boiling point of water. Okay, so this is between the melting point of ice, H2O ice, and the boiling point of water and the boiling point. H2O. Okay, so because of this, you know, you choose it this way, and because of this, you know, Kelvin scale, let's say Kelvin scale, Kelvin scale is linear in Celsius scale. Okay, because of this, the way we choose this R. Okay, and if you're interested in thermometry, there are lots of things to read. There are lots of, and I should emphasize this is a very active, at least people are running big business on this. People want to know the temperature accurately, and there will be a lot of knowledge going into calibration and how do you do this kind of calibration. And the other thing I should quickly mention is that this kind of behavior, this is based on physics, really. This is because your material has a gap. So you have a, when you have a gap, the carrier will freeze out and you have this diverging resistivity. Another thing you can do is to remind yourself the Curie law. Curie law has this 1/T dependence of susceptibility. Okay, suppose you can measure susceptibility, you have this very strict 1/T behavior, and 1/T is a very nice property we want at low temperature, because the lower the temperature, the larger the change. So that means the sensitivity increases. Okay, that's another way to build thermometer. Okay, so let me finish this. And that's about it. And later we are going to talk about thermometry again. We are going to establish the temperature scale by using the Carnot cycle. So we are going to build a heat engine. And using the heat engine, we will have a very elegant way to define temperature. Okay, so this will be next week. It won't be too long. Okay. All right. Now this is the end of chapter 1, and we can start the first law. If you have, do you have a question? Okay, so I'm going to start the chapter 2. You also have the notes. And one thing I'm doing it, the way I do the notes is the following. I will upload the draft, which what I call the draft. And you can find everything on Blackboard. And if you have questions about the note, let me know. I will address, and I will replace it with another version. If not, then the draft will become the final version. Okay, so all this draft is there for me to invite you to collaborate with me, so we can come up with a version that everybody likes, or more complete version. Okay, so the draft for chapter 2 is also there. Okay, what is first law about? First law is basically about the conservation of energy. So this is really, this is an extension of conservation law, conservation of energy, conservation. Okay, but conservation of energy is not, now this requires a little bit more work. So this is the conservation of energy when you include, when you consider heat flow. Okay, so historically, this is kind of the formalism. It really recognized heat as one form of energy. So historically, when people talk about heat, it was a difficult concept, right? People didn't know how to deal with heat and what was it. And therefore, before trying to understand heat, one thing is the flow is interesting. To understand heat, because heat is a little bit more abstract and people know a lot about work before, people knew a lot about work. So one thing you can do is to play some trick, and the trick is either ironic. So the trick is you ignore what you don't know first, and then you spend time to understand what you know and try to build up the picture this way. So you cannot ignore it forever. You ignore it first, and then later you put it back. If you read the textbooks, if you read Steen or Atkins, and this is how they develop this. Okay, if you read Blundell, this is very fast. A lot of historical part is not included. Okay, but I'm going to spend a little bit of time on this. So I will do what people did historically, and the most famous one, the most famous scientist who did this is the one who has the unit of energy attached to him, and this is Joule. Okay, so this is the strategy he adopted in 1800s. So more exactly, this is 1840. So what did he do? He said, okay, I'm not going to worry about heat because I don't know much about this. So what I will do is I'm going to perform work on thermally isolated system. Okay, so the heat cannot enter, but I can try to do work on my system. This system is otherwise thermally isolated to the surrounding. And I'm going to do work, all kinds of different ways to do work to see what happens to my system. Okay, so this is the strategy. So look at thermally isolated system. As I mean, thermally isolated system, and this isolated system turns out to be water. And the observation is this: he measured some fixed amount of water, and he measured the temperature of the fixed amount of water. And this measurement is done by different ways of doing work on the system. For example, I give you some examples here. This is from Steen. All these textbooks are available to you. I invite you to look at them. Okay, suppose you have to imagine this. This picture is not drawn quite well. Just imagine the piston and the cylinder are thermally isolated to the outside world. So you cannot really transfer heat directly. So if you want to affect this thermodynamic system inside, you can do work. For example, the work we have been talking about, the PDV work. You apply pressure, you apply force, and then look at what happens to the temperature change. This is one way to do work. Another way to do work is this. You can imagine having a stirrer here, and then you stir it. Right? This will also do work to the system. Another way you can imagine is you can have a heater here, okay, and then you have a connect to the battery, and you push the charge through this resistor, and that will also change the property of the system. Okay, now here, if you are usually I should receive some complaint about this picture here, because now I use the word heater. You might say, yeah, they will say heat cannot enter, but you are really having a heater inside, so heat enter. But remember, the way to look at this is the following. When you look at this picture here, you should imagine it to be some kind of to be some kind of black box. You do not really know what is inside. So this cylinder, this entire system is not visible to you. Okay, the only thing you know is you have a battery, and the battery is pushing charge around. So this is, in some sense, is doing work. It's just like you are pushing a piston for some direction. If you have a battery, you connect the battery to whatever device that is inside. Right? So from the battery point of view, you are pushing some charge around. This is doing work. Okay, so we regard this as work, just like steam. Actually, steam has an example, has an explanation like this. Okay, so you regard this as work. On the other hand, if you, for example, if you redraw this, you enclose this system, and you thermally isolate this as much as you can, but at one point you have a link, a thermal link. At this point, you link it to this device. I'm going to draw it. This is your device, exactly this device. In this case, we treat this as heat. So this is the example of heat. This is the example of work. Okay, so this is some kind of thermal link, and this is your heater. You heat from here, and this is an example of heat. But in the end, the message for you is this: after we establish all this, you should hopefully have this feeling that heat and work sometimes are not very easy to differentiate, and this is exactly the point. So first law eventually wants to send you this message. What I really care about is the internal energy of the system, and whether how do I change the internal energy of the system? I can either perform work, or I can add heat to the system. So in some sense, these are kind of equivalent, and it established this first line here. So first law is about the conservation of energy to include heat flow. Okay, so this is a little bit of some small subtlety that I have to explain. Okay. Now I think, what about we have a break, a 5 minutes break, and then we continue this. And the aim is to establish the internal energy as a function of state. Okay, that's my goal today. Okay, so I propose we have a few minutes break, come back at 12:35, and we will continue from there. Okay, welcome back. So here, one thing you probably remember is from last week, I use a bar to denote work. This is true. In general, work is not a function of state. It really depends on how you perform the work. Okay, so here is a statement for you. So this is true. I already wrote it down last time. So in general is path dependent. So you really have to know how to do the work. But what was found is the following. If you thermally isolate your system, that is to say you have the change. When you thermally isolate your system, you do work on the system, and the system undergoes some changes, and this change is an adiabatic change, which means no heat flow, no heat exchange. And in that case, the experimental discovery is such that I'm going, okay, be careful. Let me change the color for you. So when you talk about the work done under the condition of adiabatic path. The simplest way is to thermally isolate your system. Then this can actually be denoted by D rather than D bar. Okay, so this is path independent. Okay, so this is, I have to emphasize this. This is an observation. If you read all this thermodynamic textbook, this is really, for those really specialized book, they really emphasize that this is based on observation. This is based on experiment. And of course, in the modern days, you have very, we are talking about 1800s. In the modern days, you can do things very accurately. And so far, there is no violation of these laws. Okay. So in this case, think about this. If this is path independent, this becomes a function of state, right? This W becomes a function of state under this condition. So we can define a function of state. We are going to define a new function of state, and that is internal energy U. Okay, so this internal energy is a function of state, and therefore, if I want to talk about the change of the internal energy when the system is taken from state B, from state A to state B, I can simply write this. And how do I cause this change? If I thermally isolate my system, I can actually use work. I can actually do all kind of funny work to have this kind of changes. And this change, I can just use the internal energy at the endpoint minus the at point B minus the internal energy at point A, and this difference will tell me the change of the internal energy. Okay, for example, this is another one from your note. Okay, you see, I highlight this adiabatic path for you. Otherwise, if you are not careful when you revise this, you might get confused. You might say, hey, this if I look at the area under the PV curve, they are all very different. How can they have the same effect? Okay, but be careful. This is we are talking about different ways to do work. For example, you can imagine a system like this. You can imagine a hybrid of these two, right? You can. It's not that difficult to draw a piston like this. At least in your mind, you can do that. So that gives you different ways to do work, and they all add up. Okay, so you have a sum of different terms, and each term tells you a way to do work. And this is about first law. The first law, the work component, is really coming from the observation on how many ways you can perform work on the system. Suppose you have two ways to perform work on the system. Let's say these two. Then you can imagine you can compress it first. Then you can heat it up by keeping the volume constant. Okay, let me say this again. I can easily imagine a way to change the state of the system. And my proposal is this. Let's try to first compress it. So the volume will decrease. And I'm going to switch on my battery, and I'm going to keep this volume constant. I have a piston. I can arrange the experiment this way. Okay, in this case, what I have is this path here from 1 to A to 2. So I'm going to compress it so volume goes down. And I'm going to keep the volume and try to perform work on the system by some kind of a heater, electrical heater. The one in the middle figure in the previous slide. And that would bring me to state 2. Okay? And if this is adiabatic, the change of internal energy will simply be given by the internal energy U at 2 minus the internal energy U at 1. And if I do it differently, if I first turn on the heater, then I compress, or if I first turn on the heater, then I compress, then I will have this line here. I will have this 1B2. Or I can come up with a scheme that combine them in a funny way. So in all these cases, I will have the same change of internal energy. Okay, and the precise word of saying this is the internal energy is a function of state. I don't really care how you go from 1 to 2. I just care whether I'm at 1, whether I'm at 2. Okay, so the internal energy U is a function of state. When I have adiabatic condition, let me emphasize this again. All these are conducted with the fact that I cannot have other way to do it, to have heat flow that I cannot take account of. So this battery is a way for me to really count how much heat I put in. Okay, now if you remove the constraint, then I need to have the adiabatic path. Then the difference between delta U. I know the change of the states by going from 1 to 2, and I have a way to do the accounting for the total work done I put in. But the only thing I remove now is I no longer thermally isolate my system. Then in this case, these two do not need to be equal. And the difference is just called the heat. Okay, so historically, this is how the notion of heat was developed. Okay, so in thermodynamic, at least in physics course, we like to do it. We like to do it this way. We like to make U to be more fundamental, and then we are going to come up with the statement that if I want to increase the internal energy of the system, I can either do work or I can add heat. Like this morning is very cold, right? It was very cold, 10 degrees. So you can increase your internal body energy, your internal energy of your body by either doing work. That is to say, you can take your hands and you can rub it, right? So that is, you are working. Or you can put your hand near a heater. So both of them will increase your body temperature. Okay, so this is basically essentially the first law. And once you write it this way, there's also an advantage. As I say, sometimes it's not really easy to tell whether a given process is heat or work. But this statement kind of put them on equal footing. Or then in the differential form, we write it like this. In the differential form, du really is a d without the bar, has two contributions. The first one is d bar q, which also depends on the path, plus d bar w. Okay. And if you have different ways to perform work on the system, then you need to sum over all the different contribution. Okay, so the standard way is, for example, if you have different ways to have the generalized force on the system, and you look at the change, the reaction due to this force, and this is the way to have the generalized work. Okay, so this is the most general form. For example, you can, and this is summing over all kind of different ways to do work. If you have n different ways to perform work on your system, this is the most general expression. One way would be this piston cylinder device. This is also called the work done by hydrostatic pressure. In that case, so for example, you can, for for piston cylinder system, we can take our x to be minus p and xi, little xi. Sorry, there's no I anymore. I'm just gonna look at a specific term. The little x can be v. Okay, so in that case, your work done will be minus PDV, very famous PDV work. Sometimes it's simply called a PDV work. Okay, sign convention. Sign convention, very important. As I already mentioned last time, if you pick up a different textbook, the first thing you do is to check this sign convention for the work term. So for physicists, we like to learn more about work done on the system. So we define plus, so plus here, plus to be, plus means work done on the system. On the system. And for particularly actually for engineers, they like to use the different one. They usually have the minus sign. If you pick up a book which is more engineering oriented, they want to know about the machine, right? They have the engine, they have the machine. They care more about work done by the system. In that case, now it's very usual that we don't like minus sign, so they define it differently. Okay, the first term is less problematic. Usually, in most of the books I have seen, plus means you transfer heat to the system. Transfer heat to the system. So this is not so problematic, but this is very problematic if you are not careful. Half of the books might define it the opposite way. Okay, so since we are talking about this, let me go to that table, which I already showed you last time. You can have different ways to perform work, and that depends on your problem. For example, for hydrostatic pressure, I just mentioned, you choose your x to be minus p and little x to be v. Okay, and this table is the same as the one I gave you earlier. Now remember, last time I told you about this intensive and extensive variables. I gave you something similar. So the idea is if you take the intensive variable as the force term, that is the easiest way to imagine the work, right? So this is how you learn the work before. If you take a wire, you pull it with force F, and there's some change in reaction to this force, and the change turns out to be the extensive component of that, of the conjugate pair, and you form the work done like this. Okay, the other thing you should pay attention is here we mention this reversible. Why do we care about this? Maybe this is something you can think about first. Okay, here infinitesimal is not that difficult to understand because we want to talk about differentials. So that automatically want us to look at a very small changes. But why do we care about reversible? Okay, so I encourage you to think about this. In particular, you can use the hydrostatic case to think about this first. The answer is actually in the note, but please spend 5 minutes to think about this before looking up the note. Okay, I want to go back to here, this slide, this picture, to give you a little bit more about this, sorry. I don't know why this is being dragged. I want to talk a little bit more about this. This won't be too long, but it's interesting. Okay, so these three cases here, we can actually differentiate between two different types of work. Two different types. These are all work, okay? Two different types. One is called configuration work. So one is configuration work. So this is one. The other one is dissipative. Okay, now configuration work. This is also related to the question I asked you to think about. Why do we care about this reversible? Okay, configuration work turns out to be, this type of work is reversible. Okay, the reason this is configuration is the following. The reason we use this term is because we can express the work done on the system by the parameters of the state if the changes are reversible. Because of the reversibility, we can express this work by the configuration, by the parameters of the state. Okay, so let me write this down so we can express the work done on the system by the system's parameter. So in this case, for the third one, it will be the pressure P and V, and these are system parameters. Okay, and this is reversible. Okay, and then you can, I already give you some hints. Then you need to understand under what condition this can be, the reversibility will fail. Okay, dissipative work is not reversible. And it turns out that this is a nice way to demonstrate two types of work. So this one, because of the reversibility, you can actually extract this work, right? So if you push, you do work on the system. Suppose you have a way for the system to expand, you can actually extract work from here. Okay, so this requires reversibility, right? The way I say this is already very clear. If you take a video of the process, okay, the video of the process is this. Suppose one of your classmates is pushing this piston down, you do work on the system. And if you rewind this video, everything makes sense. And you can imagine the system expand, and this allows you to do work on the external system by pushing the piston up. Okay, the other two are not possible, right? Now, why is it not possible? This is actually very cute. Suppose you turn the stirrer, right? What happens when you turn the stirrer? The stirrer is spinning. Let's say it's spin clockwise. You take the video of this. You are really doing work on the system. You turn, and this is not difficult for you to imagine, particularly in modern days. You know, if you turn, if you stir by this stirrer, you can heat up the system, the water, right? So from the point of view of this torque outside, this T is a torque. You are doing work. You are really doing work. You have angular displacement. You don't know whether it's a stirrer inside. I tell you so, but from your point of view, you are really taking this handle and you just rotate. So there's a torque, there's an angular displacement. So you're doing work. Okay, now suppose you take the video of this and rewind this. Unfortunately, if you rewind this, you are originally you are spinning clockwise, and you rewind this, you are spinning counterclockwise. In both processes, you are actually doing work on the system. There's no way for you to reverse the process and extract work from the system. Imagine if you can, that would be scary, right? You rotate clockwise, you are heating the water, and you rotate anti-clockwise, the water is you are transferring work out from the system. You're extracting work. That is impossible. So this type of work is dissipative. Okay, so I can even give you the example would be this stirring. The work will be written as tau d theta. Okay, and how do you reverse this? You reverse, the way you reverse is you reverse this theta. Okay, how do you do that? You also, when you reverse theta, you also reverse your tau. Both of them change sign. So you have a minus sign here, you have a minus sign here, they cancel. So the work is always on the system, positive. And the other thing is electrical work, this one, electrical work. Electrical, the middle. So here you have dW is I square R dt. Here it's the same. It doesn't matter whether you push the charge this way or you reverse the process of pushing the charge this way. It doesn't really matter. You will still do work on the system. There's no way to extract work by reversibility, by reversing the process. Okay, so I think this is nice. This is something to keep in mind. Okay, any question here? So let me organize the slide a bit more. Okay, next, we want to, the most useful one for us is the PDV work. So that is this piston device. And we are going to, I would say we are going to spend the next 4 chapters thinking about the piston cylinder setup. Then we are going to spend 1 chapter to talk about different type of work. So there we are going to start from the first law again. After we know all this mathematical structure, we're just going to replace the work term. And the first law can be rewritten very quickly and all the mathematics follows. So we are going to focus on hydrostatic pressure, work done by hydrostatic pressure with the piston cylinder system. Okay, so this therefore requires some attention. We need to look at this closely. Okay, so this is the drawing is like this. Okay, suppose you apply some force F. If you push this piston by the force F, let's say originally it's here and you push it to here, this is your dx. Okay, so if you know the area, the force, this force is related to the area and the pressure. Okay, so if there's no friction, you can really relate the pressure of your system and the force you apply. If there is friction, this is the problem. And this is what I ask you to think about. This is also related to whether a particular process is reversible. Okay, and you can already sense where this is going, right? Because if you have a friction, you have loss, and this is a dissipation and the work. What happens to this force, and and the pressure. Okay, so suppose there's no friction. This is an idealized system, no friction. We are going to discuss this scenario, no friction, and we are pushing a body of fluid. How much work do we get? How much work is on the system? So this is according to our sign convention. Okay, the work done because of this is F times dx. And this can be related. Okay, let me write this down slowly. So this is this force can be related to the state variable P of my thermodynamic system if there's no friction. So I will have this relationship. But when X increases, the volume decreases. So this is where this minus sign comes from. Okay. Now the good news is this. This is something I many years ago when I learned thermodynamics, I find it a little bit striking. It doesn't matter how you define the sign convention for d bar W in the first law. Okay, listen carefully. It doesn't matter how I define that. So there's another version of the first law that write du is d bar Q minus d bar W. Okay, I know this is not our convention. So this minus sign is not our convention. Convention. Okay, we define it with a plus. But when I sit down with my engineer friend, we are going to agree that when we have a situation like this is the same. If you have a plus, if you have a minus, doesn't matter. We are always going to have this minus PdV. Okay, try it. You can try it yourself, and this is going to be the same. Although we mean differently when we define it this way, but when this expression will turns out to be the same. Okay, so so this is the same. So this is first striking point. If you are not careful, you get confused. You say, how is it possible? But you have to really think through this. Okay, and therefore you must not remember this minus sign. Otherwise, whatever book you pick up, you are wrong, very wrong. Okay, and another thing to look ahead is this. We are going to later here for the PDV work, we already have a way to write it in terms of exact differential dV. And first law will be more powerful if we can write this dq term in terms of exact differential. So we will learn that this requires us to introduce the integrating factor for d bar Q, and that turns out to give us this exact differential, which is related to entropy. So the first law reads is like this. Okay, this is the first law and second law combined will give you du in terms of ds and dv. And from here, later on, as I said, we are going to develop our thermodynamics using this, and we are going to head to one equation, which is called the Maxwell relation. And if you mess up with this minus sign, you get into a very dangerous situation where all this Maxwell relation will be wrong by -1. Then the calculation will be very wrong. Okay, so don't forget this. Don't forget this. Although here it might look very innocent, very easy, but you will get a lot of mistakes if you ignore this. Okay, so with this, we can already do some calculation. So let's try something before the end of this lecture, some very quick one. Okay, example 1. I want to know how much work is done when I compress 1 mole of ideal gas. Okay, so let me define the system for you. I'm going to use this PDV work to do thermodynamics. I still need to specify what I put inside. So my system is 1 mole of ideal gas. Now, the reason I always like to specify 1 mole is because I don't like to carry this little n around in my equation. Okay, so it's understood that I'm talking about 1 mole of ideal gas. Okay, I'm going to, what do I do? Okay, the process is I want to compress my system, compress the system. And the question I have is how much work? How much work done? If I compress from V initial to V final. Okay, can you do this? Actually, this is a yes/no question. I want to ask whether you can do this. You don't have to do it. You just tell me whether. Actually, let me put it more precisely. Can this be done? It doesn't need to be. It doesn't need to be you who is doing this. Okay, can this kind of calculation be done? Yes, no? More? Okay. Okay, why no? The answer is correct. This cannot be done. Thank you. Okay. But Harry, you say yes before. Okay, this cannot be done because let me stress this. When I ask for how much work done, I need to integrate my d bar W. But how do I integrate without knowing the path, without knowing the constraint? Okay, now you look at the PowerPoint. Okay, fine. So here we need to specify the constraint. That's why I write it down like this to trying to fool you, and hopefully you will be fooled. Then you will learn, you will remember this forever. So I need to specify the constraint. So for the example 1, this is isothermal. Okay, then this is kind of specifying some kind of path. I'm going to move along a path that the temperature cannot change. And the other one for ideal gas, another common one is the same thing, but with adiabatic condition. So let me, I don't want to write again and again. So for example 2, this is what we will have. So this is example 1. Example 2. Example 2, we are going to do adiabatic. Okay, and you are asked to calculate this. Okay, let's start from 1. Very simple. So when you have the path, you will be able to calculate the work done. And that requires integrating from the initial point to the final point of d bar W. Okay, d bar W, remember, we have this minus sign here. Okay, so if I tell you this is an ideal gas, we have minus RT and 1 over V dV. Okay, so this is using the equation of states for the ideal gas. And because it's isothermal, this T can be pulled out. And that's it. This is what I need to integrate. And you will see the answer will be RT log of VRT I divided by Vf. Don't forget this minus sign again. That's why this has to be a flip. Okay, and then you should check. You should do some check to see whether this makes sense. I told you the way I define the problem is this. If I have a work done on the system, work done on the ideal gas, then this has to be positive. Okay, so now I'm compressing the system. I'm compressing the system. I'm moving the piston inward. So the volume will become smaller than the initial one. Right? So this term, the volume will become smaller. So the original volume is larger. So this log term is positive. So the whole thing is positive if I have compression. So this is so this whole thing is positive for compression, so which is correct. And we know compression means I'm doing work on the system. Okay, so this is one. And the second one is example 2. Adiabatic. This is for adiabatic condition, what is the formula we need to know? We need to know the product of P times V to the gamma is a constant, in addition to the equation of state for the ideal gas. Okay, so there's this one, and of course the equation of state for the ideal gas. Okay, where this gamma is adiabatic index. And this is related to the ratio of the heat capacities, and something you will see on Wednesday. So how do we do this now? I tell you the path, so I can in principle calculate the work done like before. So I have my, I have to integrate from the initial to final. I have PdV, and I'm going to call this constant C. So I don't need to, maybe K is better. C looks like heat capacity. Maybe K. Okay, so what do? I have this minus sign. I integrate like this. P will be constant divided by V to the gamma dV. Okay, and the rest are just high school mathematics. So some high school mathematics, and you get the answer in the notes. So in the end, you get something like this. Please try. Although it's high school, please try. Sometimes I set some questions like this in the midterm. People will still make mistake. Okay, so this is the final answer. Okay, I think that's enough for today. So my request is for you to try this, and so you get very comfortable with this kind of calculations. And next time we want to talk about more complicated calculation. All right, so next lecture on Wednesday, we are going to introduce heat capacities, different kind of heat capacities. Then we are going to learn how to relate heat capacities. And we are going to revisit the problem of ideal gas expansion. Now you are doing compression, right? I want to talk about expansion. Why do I want to do that? Because later I will be able to talk about, now you have the compression, if we have the expansion, we can form the Carnot cycle. And that is something very important for motivating the second law. Okay, and then I'm going to hopefully next on Wednesday I can introduce the concept of enthalpy and free expansion of ideal gas. So there will be a lot more things to do, a lot more partial derivative we can play with, and that will be the roadmap for this chapter. Okay. All right. Thank you very much. See you on Wednesday. And if you have a question, please raise your hand and I will wait for you.